lecture. Yeah, good. Okay, fine. Let's continue. A diesel engine and a gasoline engine. They both of them use the combination of piston and cylinder to convert the chemical energy from combustion and the heat energy absorbed by the combustion gas, and finally it was converted into the useful work output by using the combination of piston and cylinder. This combination help you achieve this purpose, this goal, right? So actually, they are sharing the same working principle. By using the reciprocating motion, you can convert by compression, expansion, by the compression, combustion, expansion, and exhaust the exhaust of your burnt gas. You can achieve the conversion from the different energy. This is a function. Actually, there is another type in our daily life, the internal combustion engine. That should be a gas turbine. It is usually used in aviation, in aircraft. Essentially, the working principle is a little different with the gasoline engine and the diesel engine. Actually, it is a rotatory machine. By the axial motion of the air flow and from the compressor, the combustion chamber, and the turbine. It helps you convert the chemical energy into heat energy and then into your work output. We don't want to talk too much about the gas turbine. If in the future you may take a course, the aircraft propulsion system, you may run this kind of engine. Here, let's go back to the diesel engine. As I said, this engine is quite similar with the gasoline engine, except the ignition system. The major difference is that diesel engine use self-ignition system, or we call it compression ignition system, while the gasoline engine use a spark ignition system. Gasoline engine use a spark as its heat source, but the diesel engine do not need a heat source. The difference, this is a major difference. This major difference causes a much higher compression ratio for the diesel engine than that of the gasoline engine. In the previous lecture, you have learned efficiency of the air stand Otto cycle. It is directly related to what? Temperature, right? The temperature at each point. Temperature during the process is directly related to what? To compression ratio. That means a higher compression ratio can give you a higher thermal efficiency, right? That's the relationship between compression ratio and your thermal efficiency. When we perform a cycle analysis, Our major concern is the thermal efficiency. Of course, we want to a higher thermal efficiency, right? So you may ask, can we use higher compression ratio can give us higher thermal efficiency? Can we just increase the compression ratio of the gasoline engine? The answer is not. We can't. Because if we increase the compression ratio, we will start stepping into a big problem. We may encounter a phenomenon, combustion detonation. Sometimes we call it knock. This phenomenon, in Chinese, it should be, point to you, should be combustion detonation. It is really very, very bad to your engine. We should always avoid it. The reason why we call it knock. That is a phenomenon that your combustion happens before your spark even goes off. Because the high pressure and high temperature of the compressed air, it will cause a self-ignition because the temperature beyond the self-ignition temperature. If you listen to the engine, you will hear a sharp noise, the mechanical sharp noise, bing bong. We should always avoid this phenomenon because it's really very, very bad to your engine. We don't want it. So we cannot compress too much of the gasoline because gasoline, although the self-ignition temperature of gasoline is higher than the diesel, but it is not stable as diesel because it's lighter, because the density of the gasoline is smaller. So we cannot compress gasoline too much. We cannot use it by using the compression ignition system. But we can use it for gasoline, for diesel fuel, because it is more stable than gasoline. In order to avoid the phenomenon of knock, what we will do, instead of the intake, the mixture of air and fuel, is joined into the cylinder in the inlet, the intake stroke. Here, we don't use a mixture of diesel and air anymore. Instead, air is taken into the cylinder. Sorry, should we use this one? Taken into the cylinder, and we compress the air into high temperature and high pressure. The temperature can reach as much as 600 degrees C to 800 degrees C. Then what we will do is what next by using this injector, we inject diesel into the cylinder to avoid the knock phenomenon, the detonation. Because the self-ignition temperature of diesel is about 210 degrees C. The compressed air now has high has a high temperature and high pressure, about 600 to 800 degrees C. So therefore, after the injection, the diesel, the self-ignition will occur, so that combustion occurs. That's the major difference of this gasoline engine and the diesel engine. Although professionally have already taught you, right? Although we cannot use a very high compression ratio for gasoline engine, it still has its advantage, right? Because you use smaller compression ratio, you can use smaller cylinder, right? Smaller stroke, smaller displacement. That means it can give you faster speed, right? High speed. And also, the working process of the gasoline engine is much quieter and smoother than the diesel engine. Diesel engine also have the drawback of high pollution. It is a highly polluted engine. But with the high compression ratio, you can get higher thermal efficiency and higher work output. They have their own advantage and own drawbacks. Okay. In the last lecture, you have already learned the construction of a typical engine. And also you know the 4-stroke spark ignition engine or gasoline engine. So now let's go through the 4 strokes of the diesel engine. Let's have a look at the working process of the compression ignition diesel engine. At the starting point, there is nothing inside your cylinder. You have both valves, the intake valve and the exhaust valve. You keep both valves closed. And the piston at its top dead center, the highest position, you cannot go furthermore. The highest position inside the cylinder. And then we start the journey of the working process. From the starting point, now we open the inlet valve, and the piston moves downward to increase the volume between the cylinder and the piston. To join in the air, you should pay attention here. We use air only. Here, we use air only. Gasoline engine use a mixture of air and fuel, but for diesel engine, we compress air only. So in the intake stroke, we only join air into the cylinder. Join air into the cylinder, the piston now moves all the way to the bottom dead center, the lowest position inside the cylinder. It cannot go further. That is the dead end. Now your cylinder has full of air. Now we start to compress our charge, the air, to increase the temperature and pressure. The piston will give a work input through the crankshaft and connected by the connecting rod. The piston moves upward to compress the air inside your cylinder. This piston moves upward towards the top dead center. The air is compressed into high temperature and high pressure. Towards the end of this compression stroke, by using the injector system, by using this injector, diesel is injected into this high pressure and high temperature air. Diesel fuel is then vaporized to initiate the auto ignition, because the air is high temperature, which is above the self-ignition temperature of diesel fuel. Combustion occurs. By injecting the diesel fuel, you should pay attention here. At a gasoline engine, what we assume the constant volume combustion. Professor Liang have told you that because the combustion is very fast, the time is less than 0.01 seconds. So we can ignore the movement of the piston. So what we have is constant volume combustion. But here, for the diesel engine, we no longer have the constant volume combustion, because the piston moves during the combustion process. The piston moves downward to give work output. That is a constant pressure combustion. We keep the pressure as constant. We can assume the pressure is constant. So sometimes we call it constant pressure combustion. For gasoline, we have constant volume combustion. The burnt gas absorbed the released kinetic energy from the fuel, observed the heat energy, and then push your piston downwards to give you useful work output. By using the connecting rod, the piston is connected to the crankshaft. By this way, we can convert this representing motion into rotational motion, which is much easier for maybe you need to transfer it to the transmissions in your vehicle. It's much easier for us to transfer this rotational motion. Then we obtain the useful work output. After the combustion, what we have inside the cylinder, it should be the burned gas. This gas now is useless because from the second thermodynamic law, you can never convert all the heat energy into useful work. Remember that? Feel that this exhaust gas, we call it exhaust gas because it's useless. It cannot give you work output anymore. We need to discharge it. We need to drive this exhaust gas out of our cylinder, because if we keep it inside the cylinder with the accumulation, it will boom, explosion, right? So the last stroke is the exhaust stroke. This exhaust valve opens. The piston moves upward again to drive the exhaust gas out of the cylinder. We discharge this exhaust gas. The piston moves upward until the top dead center. Everything goes back to the initial state, goes back to the starting point. We can start another full stroke again. By repeat these full strokes, we can obtain the continuous work output. We can obtain the power for our vehicles. Intake stroke, we join air into our cylinder through this inlet valve. The piston moves downward to expand the volume to let you join the air in. Then we compress the air by the upward motion of the piston with a work input. The air is then compressed into high pressure and high temperature. Towards the end of this compression stroke, diesel fuel is injected into cylinder through this by using the injector. Diesel fuel is then vaporized to start the self-ignition. Combustion occurs. The chemical energy inside the fuel is released and turned into heat energy, which is absorbed by the combustion gas. The high temperature, high pressure combustion gas is then push your piston down to give you useful work output, to produce power for your vehicle. That's the expansion stroke. Sometimes we call it a power stroke because in this stroke, we can obtain power. We can obtain the work output. The useless gas, burnt gas, now we call it exhaust gas. We'd like to drive them out of our cylinder. So piston moves upward again to drive this exhaust gas through this exhaust valve. Everything goes back to the initial state. We repeat this process, these 4 strokes to get continuous power, continuous work output to drive our car or to any machine that you want to use, you want to drive. You should pay attention here. In the intake stroke, we draw air into cylinder only. We use air only. In gasoline engine, we use a mixture of fuel and air. And instead of using a spark ignition system, we use an injector to inject the diesel engine. Towards the end of the combustion stroke, the diesel fuel can start the self-ignition to initiate the combustion. That's the major difference of gasoline engine and the diesel engine. Also, in the power stroke, in the expansion stroke, what we have is a constant pressure combustion. Gasoline engine can ignore the movement of your piston because the combustion is very fast. The moment is negative, but here we can't. During the combustion, we keep extracting the diesel fuel, and the piston moves downward to give you work output. So that's the difference. You need to remember this difference, okay? At this point, any problems? Any problems? If no, I will continue, okay? In the previous lecture, Professor Liang explained to you why we need an ideal model to analyze an engine, an internal combustion engine. Because a real engine, the process inside a real IC engine is complicated. Because we have two things combined together. That is the chemical energy, the conversion of chemical energy into heat energy by combustion. And also the heat energy, the conversion of heat energy into work output. Combine these two together inside a real engine cycle so that we have two efficiency. Combustion efficiency and thermal efficiency. Combustion is not perfect, right? You know, in reality, we don't have perfect things. Combustion must have an efficiency. But when we have a look at the cycle, when we perform analysis for cycle, our major concern is thermal efficiency. We want to have a look at the engine itself, but we don't care about the combustion process. We don't care about the combustion efficiency. So we have to delink these two things. Delink the combustion from our thermal efficiency. Delink the combustion efficiency with the thermal efficiency. We put combustion aside so that we can focus on the thermal efficiency, focus on the cycle analysis. As an engineer, when you met a problem, you want to perform analysis for your problem. The first thing you need to think is how to simplify your problem, because in reality, a real problem is quite complex, right? The first thing is you need to identify your problem. What's your major concern? Then you should ignore other things. You put other things aside and focus on your own concerns. So here, our major concern is the thermal efficiency. So we try to eliminate the influence caused by the combustion. So we built up an ideal model for our engine to perform the basic analysis for our cycles. We know it's not true, but we have to do it to perform our analysis. Also, we assume air is the working fluid. The working fluid is always air inside our cylinder. It remains unchanged during the whole process so that we can ignore the intake stroke and the exhaust stroke, because we always have the same amount of air inside our cylinder. That's the first and the second assumption. First, we ignore the combustion. We assume our combustion happens outside the cylinder. We use a heat supply and heat rejection to model the combustion and model the exhaust, the exhaust gas. Second, we assume the component do not change during the whole process. We only have air or the working fluid. It remains unchanged during the whole working process. Air, you can assume it as perfect gas. So you can use a property of perfect gas, right? Then we assume there is no loss. Ideal model means no loss. It's not true in reality. But to perform the basic analysis, we assume we have ideal model, which is no loss, so that we have what? Reversible process. We have reversible process with the assumption of no loss. For the loss, we have no heat loss and also the any loss related with the motion, the flow, the fluid motion, the fluid flow. We assume there is no loss. So by these assumptions, we have this air-stand diesel cycle, just like what we did for the air-stand Otto cycle. We make assumptions and build up an ideal model to perform the basic analysis, to have a look at the thermal efficiency. That's our top concern, right? So, because it is not true, it is an air-stand cycle. It is ideal model, so that you should keep that in your mind. The starting point is not the same as the real engine cycle. For a real engine cycle, the starting point is the piston at the top dead center. There is nothing inside our cylinder. That's the starting point of a real engine. But here, for the air-stand diesel cycle, what we have is we assume at the starting point, this cylinder is full of air, and the piston at its bottom dead center. Excuse me. This is the starting point of our ideal cycle. You should remember that it is not the same as that of a real engine. Now we are going to have a look at the process for this air-stand diesel cycle. We have air inside. We ignore the intake stroke and exhaust stroke, so that what we have now should be a closed system, right? Closed system. That is non-flow system. The amount of air do not change during the whole process, during the whole cycle. So it's non-flow system. Non-flow system, what you can use is non-flow energy equation. Remember that? In chapter 1, you have learned this non-flow energy equation. That is the difference between your heat and work equals to the change of what? Yes, internal energy. Sorry. I'm sorry. I forgot to turn off my my phone. Non-flow system, you can use non-flow energy equations. Okay, process 1 to 2. We call it isentropic compression. We'd like to compress the low pressure air into high pressure air by giving a work input. We assume it is an isentropic process. What is isentropic? Isentropic means no heat, adiabatic, and reversible. And also this process, you have characteristics. It should be PV to the power of gamma equals constant, right? That's the characteristics of this process. During process 1 to 2, the piston moves upward to decrease the volume inside the cylinder so that the low pressure air is compressed into high pressure air. And you also have high temperature air, right? For fluid, you always have this kind of property. You compress it, you have higher pressure, you can increase the pressure as well as the temperature, right? The piston moves upward until the top dead center. Here you have the minimum volume of your air inside the cylinder, from the maximum volume to the minimum volume. At point 2, the next process 2 to 3, we assume there is no combustion occurs inside our cylinder. So we use a heat addition instead of the combustion. We use this heat supply to model the combustion. We add heat into our system. But you should pay attention here. For the air standard Otto cycle, we give the heat at a constant volume. But here, we give the heat at a constant pressure. That means here you have movement of your piston. Your piston moves downward. You have a work output, right? Because you have displacement. That means you have a work output. You have boundary work. We give a heat supply to raise the air temperature to maximum. At constant pressure, you should pay attention. This process has work output. You have work output because the piston have movement. So piston moves from the top dead center to the location on point 3. The volume changed from the minimum volume to the volume 3, but here you have P3 equals P2. The pressure should be equal. From point 3 to point 4, that is your power or expansion stroke. The high temperature and high pressure air expands to give you useful work output. Again, we assume this process is isentropic. That means adiabatic and reversible. Adiabatic means no heat. So, showing this process, high temperature and high pressure air expands to the low pressure and low temperature air. And at the same time, you obtain the work output during this isentropic process. From point 2, point 4 to point 1, we have heat rejection at a constant volume to reduce the air temperature as well as the pressure. And all properties are back to the original values. We finish the whole cycle. Process 4 to 1 is the same as that in the gasoline engine, the air stand auto cycle. So we have in total, we have 4 non-flow process. 4 non-flow process. Non-flow because we always have the same amount of air inside the cylinder. We don't have the intake stroke and exhaust stroke. We always have the same amount of air. From process 1 to 2, we have the isentropic compression. The air is compressed from low temperature and low pressure to high temperature and high pressure by giving a work input to the system. At point 2, we start to give a heat supply. We'd like to add heat into our system to model the combustion. But you should pay attention here. It's a constant pressure process. It's different with the constant volume process in air standard auto cycle. We have a work output here. We have heat supply and work output because the pressure keeps constant. And therefore, the piston have a movement. You have displacement, definitely you have work output. Then process 3 to 4, the high pressure, high temperature air expands to low temperature and low pressure air to give us useful work output. The piston moves downward from the top dead center to the bottom dead center. Again, it's an isentropic process. There is no heat. We only have work output. At point 4, we reject heat at the constant volume to reduce the air temperature. And all the properties are back to the original values, to the original states, so that we have go back to point 1. That's the whole process of air standard diesel cycle. Like the air standard Otto cycle, you should draw the PV diagram directly whenever you see this word. So I will teach you how to draw the PV diagram, okay? This is our cylinder, right? This is top dead center. This what bottom dead center. Here we have is a piston. Here we have V1. This should be V2. For this PV diagram, x-axis should be V. P should be the y-axis. From point 1 to point 2, we go through a isentropic compression. What we have is a isentropic compression. The low pressure and the low temperature air is compressed to high temperature and high temperature and high pressure by giving a work input, right? So that from 1 to 2, it's isentropic, that there is no heat. What we should do is we give a work input to compress our air. From point 2 to 3, pay attention here, it's different with the air standard Otto cycle. What we have is a constant pressure process. Constant pressure, so that we have P3 equals P2, right? What we have is heat supply and work output, because you have movement of your piston. Here, we give a heat supply to model the combustion process, where we get the work output because the movement of the piston. By giving the heat supply, the temperature of the air is increased to the maximum. You should pay attention. We have a work output. Drawing this process. Here we have V3. So it's 0.3. Process 3 to 4, again, is a isentropic process, because isentropic expansion. because the high temperature and the high pressure air expands to give you useful work output, so that we can obtain the useful work output. The air is then changed into low pressure and low temperature. Isentropic. The characteristics for this process is what? P V to the power of gamma equals to what? Constant, right? Don't change during this process. And the process from process, sorry, here, 3 to 4. What we have is a work output. Work output. Process 4 to 1. The same as that in the air stand Otto cycle. We have a constant volume heat rejection. We reject heat as constant volume. So we have V4 equals to V1. The volume should be the same, should be constant. What we have is a heat rejection. There is no work because there is no movement. The temperature of the air go back to the minimum, and the every property goes back to the initial state. That's the process of 1 to 2, 2 to 3, 3 to 4, and 4 to 1. The 4 non-flow process. Non-flow process. Guys, you should know how to draw this kind of PV diagram, okay? And you should keep those relationships in your mind. You should know the isentropic, the constant pressure, and the constant volume process, okay? You need this kind of equations and PV diagrams to solve your problem, okay? Okay. Because it is a non-flow system, so we can use the non-flow energy equations. That is the difference in heat input and the work output equals to the change in the internal energy. That's the non-flow energy equations. Also, we have air as the working fluid. Air, we can assume it as perfect gas, so that we can use the property of perfect gas. But by combining these two, we can solve our problems. We can perform our basic analysis for this air stand diesel cycle. Sorry, here should be diesel. I should say it should for air stand cycle. Yeah, it's good. Because for air stand Otto cycle, you also use this equation to solve your problem, as well as the air stand diesel cycle. They are for air stand cycle. So you can use a non-flow energy equation and property of perfect gas. Actually, this content are in chapter 1, the revision of thermodynamics. If you are not familiar with them, go back to check chapter 1, to review chapter 1, okay? Okay, I have already shown you how to join this PV diagram. Process 1 to 2, isentropic compression, so that we have the characteristics of the isentropic process. That is PV gamma equals constant. During process 1 to 2, the state of air is changed from the point 1 to the property at point 2. From the low pressure and low temperature to the high temperature and the high pressure by obtaining a work input, by giving a work input to the system. Isentropic, no heat. Process 2 to 2, constant pressure heat supply. Pay attention here, you have a constant pressure process. It's not constant volume anymore. That is in the air stand Otto cycle. That's the major difference of these two air stand cycle. You should always remember that, okay? P is constant. That means P3 equals P2. So we give a heat supply. The state of the property of the air changed from point 2 to point 3, T2 to T3. T3 is the maximum of our cycle. The temperature is increased. The temperature of air is increased to the maximum during this process. The high temperature and high pressure air is then expands by a isentropic process to produce a work output. So the property of air changes from at point 3 to point 4. Again, is isentropic process, is isentropic expansion. Again, you have this characteristics. PV to the power of gamma equals constant. Process 4.2 is constant volume heat rejection. We reject heat as a constant volume. The temperature and pressure reduced to the initial state. Every property goes back to the initial state. Now we finished the whole cycle. Actually, this air standard diesel cycle, we no longer use this cycle because it's almost phased out. Because the efficiency is not very good. Actually, for the real diesel engine, what we have is a air standard mixing cycle. In your lecture notes, we have introduced to you the air standard mixed cycle, but here we don't want to talk too much. Actually, for that cycle, we have a constant volume here. For the cycle, the difference is that you have a constant volume process and then constant pressure like this. Should be like this. Combine the constant volume combustion and constant pressure, constant volume combustion and constant pressure combustion together to give you better performance of your engine. Okay. Okay. Now we have already drawn this PV diagram. We know the whole process. We know the characteristic. Now we can start performing our analysis for the cycle, step by step. So from change to process 1 to 2, isentropic. Sorry. It should be. Process 1 to 2, it should be isentropic compression, right? By seeing this word, isentropic, we can write the characteristics of this process. PV gamma equals constant. That's our equation 1. We have air, the perfect gas, as our working fluid. So we have the property of perfect gas. That should be PV over T is constant, right? Know that? Do anyone have problem with this equation? If no, I will continue. Property of perfect gas, PV equals MRT, right? If we rearrange it, because it's a non-flow process, the mass, the amount of the air do not change. So we have PVT equals to constant, okay? At this point, any problems for these two equations? No, no. Okay, I will move on. So what you have is a compression ratio. We usually use RV equals the definition of compression ratio is what? The maximum value over the minimum value. That should be the volume at the bottom dead center over the value at the top dead center. That should be V1 over V2, right? That's the compression ratio. V, BD, C, TDC. Right? Can you follow? Yes, okay. So from equation 1, what we can obtain is that PV gamma constant. So P1 V1 gamma equals P2 V2 gamma, right? If we rearrange it, we have P2 equals P1 V1 over V2 gamma. What this? What this? Yeah, good. That is P1 RV gamma. That is P to V ratio, right? P to V ratio. The equation P to V ratio. If we use the equation 1 divided by equation 2, what do we have? TV gamma minus 1 equals constant, right? If we plug this equation into this equation, what we have is TV gamma to the power gamma minus 1 is constant. So we have what? T1 V1 gamma equals to T2 V2 gamma minus 1. If we arrange this equation, you can get the T to V ratio. Again, this is our compression ratio. That should be right. At this point, any problem? No problem, right? It's easy because it's the contents in chapter 1. Chapter 1, okay? We have non-flow process. That should be the non-flow energy equation. What that? Q what? What's this? Equals what? Non-flow. Non-flow. Where is H? H is entropy is for flow system. For non-flow, what that? What this? Yes. This is non-flow system, so we need to use non-flow equation. That is the difference of the change of internal energy. Pay attention, okay? And you should always remember, you always use the final state minus the initial state, okay? Final state minus the initial state. Always process 1 to 2, that is U2 minus U1, okay? If 3 to 4, that should U4 minus U3. Final state minus the, sorry, I'm okay. Always remember the final state minus the initial state. Otherwise, you may cause error, okay? Isentropic means that what? No heat, right? No heat. So that this term can be rejected. We can cancel this term. If what's the internal energy for perfect gas? What? Yes. Use the property of perfect gas, use the equations. Now we arrange it. What do we have? We can calculate the work input. It should be mCV T1 minus T2, okay? That is your work input. Okay? At this point, any problems? If no, I will continue. Okay, good. No problem. Let me check the, for those who are facing your computer, do you have any problems? Let me check. Can you follow? Can you speak Chinese and point? Sorry guys, I don't know how to speak Cantonese. It's okay? You can listen? Oh, okay. At this point, for the previous content, any problems? Anywhere that should use, Chinese to explain to you which part? This part or this part? The full strokes, the working process, or the ideal process? Yes. Which one? Which one you need addition explanation in Chinese? Which one? Which one? Any? Yes, I know yes, but which one? Which part? This part? The ideal cycle or the real engine cycle? Okay, you guys, any part? No? What? That's not good. Okay, I mean, good. Trust. 这个是四冲程的压燃发动机，柴油发动机。It's quite strange to speak Chinese. I never. Okay. 四冲程。事实上 ，actually，我们有2冲程的发动机， 但是非常少见，用于那种小的 machine、small machine， 像是除草机那小小的除草机可能会用到2冲程，但对于车辆，对于 for vehicles、for trucks 更常见一些 ，common，OK。So 这里我们就以4冲程作为 example for you。所以柴油机和汽油机 gasoline 和 diesel 它们最大的不同 the major difference is 柴油机是用压缩燃烧的方式，而汽油机 the gasoline engine use a spark ignition system， 就是说我给它一个点火，作为一个 heat source， 就是额外的 heat source 去点火。因为呢汽油它虽然它的自燃点就是 the self ignition temperature 高于柴油 is higher than the diesel， 但是它性质的 property 是不稳定的，没有那么稳定 unstable，OK， 它更容易产生一种爆燃呐，就是嘣爆燃的现象，所以就是会产生一种敲缸，它对你的发动机非常的不好，你会发现就嘣冰嘣，然后而且还会它就是属于在如果你压的太多 ，if you compress too much or your gasoline， 你会得到就是什么呢？它会在你点火之前啊，你那 spark 在 goes off， 就是它进去之前，你点火之前，它就已经开始自燃了 ，self ignition 就已经发生了，所以它就会产生一种就是这种爆燃的现象，其实是不好的，你可能会造成你的发动机的这个空转的各种现象，就非常非常不好。You should always avoid the knock the detonation， 就属于你不能有这种现象的。所以呢，就是用 gasoline 一般来讲，我们都是用火花点火，但是它有好处，火花点火，然后你 compression ratio 你没有那么高，所以就是说是你那个 cylinder 啊就可以小一些，轻一些，而且它快呀，它可以动得快，因为它冲程短，这样快。这个 Professor 梁已经跟你们说过了，就是你冲程短呢，就是快，你就可以给你更高的速度嘛，对吧？但是它就是工作起来呢，你听它的声音 ，if you listen to the engine, to the diesel engine and the gasoline engine， 你去听这两个的，你非常明显的就会发现，这个 diesel engine 特别的吵，它声音特别大，而且就是那个发动机也比较大嘛。你看你坐那个 bus 啊，那个声音就很吵，但是我们如果坐家里的那种 domestic 或者是那个 household 的那种车，那种小车啊，你的声音就非常小，而且它舒服嘛，震动啊各方面的都比较小，这是它的优点。同时呢，柴油机你说我压的要压燃很高，那就代表了它的那个最高温 ，Professor 梁告诉过你们要可能达到2000摄氏度。然后我们现在没有办法压更高呢，其实就是 due to the limitation of material and manufacturing， 我们的材料还是有限制的。所以就是说，同时呢，这个柴油机 diesel engine 呢，它会更加的污染更重嘛，它烧不干净，这也是一个最大的问题。所以它们都有自己的优点，也有自己的缺点。你像是你这个汽油机就没有办法给你那么大的 power， 对吧？所以就是说我们可能就还是现在一直在做这个 research 啊、研究啊什么的，我们需要不同的优缺点嘛，都要是照顾到这样子。所以这就是他们主要的 major difference 不同啊，一个用火花点火，它的压缩比 compression ratio 会低一些，一个用这个压燃 compression ignition， 我们会让它那个 self ignition 可以得到一个高一些的 compression ratio。所以就是这就是他们最主要的不同。还有一个不同呢，就是我们一般在汽油机的时候，我们会说叫一个 constant volume combustion， 因为 Professor 梁跟你们说过，它那个燃烧非常快，它那个 speed 非常的快。它不稳定，当然它有优点，它燃烧变得特别快，然后它就会基本上你可以 ignore the displacement of your piston， 你可以忽略你的运动，就是你的你的这个活塞呀，这个活塞的你可以基本上当成它是不动的，所以就是在 constant volume 里面去发生燃烧。但是呢，这个柴油机就是你一般是一边喷油，它会喷很长时间，因为是那种气化的，就是那个油，然后喷上去，它的燃烧发生的慢一些，然后喷进去，然后它会这样子往这边动动动，一边喷一边燃烧，它会一边往这边动这个活塞，所以我们会说是一个基本上近似于是一个 constant pressure combustion， 这是他们两个的算是不同点。但事实上，他们两个其实是非常相似的工作原理 ，similar working principle， 因为它们其实都是一种用 use a combination of piston and cylinder， 用这个活塞和气缸 cylinder 的组合来帮你实现呢，就是先从油烧成热能，再从热能转换成一种机械能。然后其实它是一种这种往复运动，活塞的往复运动。但事实上，这种运动呢是不好传的。我们一般都会用这个 connecting rod connected to the crankshaft 转成一种这种圆周的这种运动，这是 rotatory movement。这样子呢，我们好往外就是用一个轴就可以传递我们这个 power。比如说会传到那个汽车的变速箱，然后再分配到不同的什么前驱、后驱的车，它的轮子里面，这是它的一个工作过程，或者它的一个 main function， 用这种往复运动来实现我们想要 power 的这种目的吧 ，our purpose。但是就是我们讲在这里呢，只用这两个作为 air standard cycle 讲。事实上，那个内燃机 internal combustion engine 呢，我们还有另一种常见的就是 gas turbine， 在发动机那个什么飞机发动机 in aircraft aviation， 那个呢就会是因为这个有个缺点嘛，你这样一动一动的，就是什么，你有的时候你会是有 power 有 work output， 但是当你比如说进气这个 intake stroke和 exhaust stroke， 你就没有那个 power， 对吧 ？power output， 所以我们一般都是用4缸、6缸的 multi cylinder， 这样才能得到一个 continuous work output。然后，但对于飞机上的发动机来说，就是这个还是太这个 work 这个 power 是不够的 ，is not enough， 所以我们会用那个 gas turbine， 它是一个那个。气流啊是一个轴向的流动，它是一个这样的结构。You have compressor 压缩机，combustion chamber 燃烧室 ，turbine 我们叫我不知道 in Cantonese 怎么讲的，我们会叫做透屏，工作透屏，就是算 turbine 吧，就是 turbine。expansion 对 expansion， 在粤语怎么说这个 turbine？涡轮涡轮，我们叫工作透屏啊，就 turbine 啊，就是其实他们为什么是IC engine 呢？就是他们都是在你的 combustion happens inside your system. You have internal combustion engine. 那其实对应的就是什么 external combustion engine。对于 external 的话，就是你从它字面的意义，就是说燃烧跟你的供脂啊 ，the working fluid 是不参与的，它是发生在外面的。其实你们学过什么 Rankine cycle，the steam power plant，your water and steam do not involved in the combustion, right？ 它不参与燃烧的，燃烧是发生的 combustion happens inside the boiler。对， 我们可以把它称之为 external combustion engine， 但事实上我们平常不这样叫它，但是其实来讲，它是可以算是这种外面的外部燃烧的，就我们不常见，不是不常，我们不用这个称呼，但是我们用内燃机这个称呼，是因为燃烧是发生在你这个机器里面的，是发生你一个 system， 其实你这个 working fluid air and fuel burned to give you power， right？ 这就是它在你这个机器里面会发生燃烧，这是我们称之为内燃机，这就是我们称之为内燃机的原因。然后呢 ，gas turbine 呢其实是另一个 cycle， 跟这个就有点不一样了。它是一个通过，但是它们有一种相似的地方，就是 Professor Liang have already taught you， 我们永远要有一个什么过程呢 ？Compression first， 我们要先压它，把它拉到一个高点，才给你更多的释放出更多的能量。所以其实它们有相似的地方，就是压缩、燃烧、膨胀、做功。Compression, combustion, and expansion to give you work output， 这就是它们的共同点。但是，它们还有一些不同，就是它们的工作原理略微有些不同，所以它们是不太一样的 cycle。所以就是这里呢，我们只讲一些，sorry， 只讲一下 diesel 和 gasoline 这个常见的这两种的 typical。的 cycle，gas turbine， 如果你学那个 aircraft propulsion system， 你们就会学到这个东西 gas turbine。燃料来讲呢，我们现在有 LPG、gasoline， 还有这个 diesel。我们其实还有另一种叫做我也不知道粤语怎么讲，那我们叫煤油，有时候叫重油，也是用在航空航天上，就 aviation， 因为它更重一些，就像是柴油，它一克是1 kilo diesel 会给你更多的能量嘛，对吧？比起 gasoline， 那个煤油呢会更重一些，所以它给你更多的那个能量，所以这是另一种的燃料，这算是我们平常最常见的一些 IC engine，OK？ 所以在这里呢，这个4冲程的压燃式diesel engine, combustion ignition diesel engine， 就是第一点就是你要注意它的进气呢，这 intake stroke we have air only， 就是你只有进气。为什么呢？我说了，如果说是你燃油的话，你压缩太多，它会爆燃嘛。所以为了防止这个问题呢，我们不再用 mixture， 我们用，当然这也有我们现在我只能给你一个 general speaking， 其实它还有一些就是不同的油它有 property 嘛，但是我现在可以这么给你解释，就是我们不再引入那个 mixture 了，我们现在是压空气，然后再往里面喷油，所以就是你们要注意，这是最大的不同，就是属于引进空气，我们引进来，然后压缩在最高点的时候，就快要到最高点的时候，我们开始喷油。这个 diesel 进来的是这个温度比它的自燃点的 self ignition temperature 高 ，higher than the temperature self ignition temperature， 所以它喷进来呢就自己可以燃烧 self ignition， 你不需要给它加一个 heat source， 这其实就是柴油机的工作原理。diesel engine 呢 ，gasoline engine 就是你必须用火花去点火。所以你可以引进一个 mixture air and gas， 然后其他它们都是很像的。你 intake stroke， 你把 air draw in， 你把 air 带进来，然后压缩它到高温高压，然后喷油 inject diesel into your cylinder by this injector， 然后它会那个开始燃烧 ，combustion occurs. The chemical energy inside the fuel is released as heat energy. 化学能 chemical energy of the fuel 转换成 converts into heat energy, right? 然后你燃烧后的气体 the burned gas absorb this heat energy， 然后就会变成更高温、更高压，可能 maybe 2000 degrees C， 然后它就会开始膨胀 expansion， to push your piston down to give you work output。然后最后呢，这个气已经没用了，废气了，所以叫 exhaust gas， 因为它不可能再给你，即使它的温度还很高，它热力学第二定律嘛，你不可能把100克 kilojoule heat 全部转换成 work， 你还剩下60%，那怎么办呢？我们只能把它排走 ，drive them out from our cylinder，drive them out of the cylinder，OK， 就是你把它要排出去，那就是说我们最后的这是一个排气冲程，所以这就是4个冲程往复的这样循环，你就是实现我们这个功能。The main function of IC engine is to use the chemical energy inside the fuel to produce you the useful work output。你去实现这个功能，你就需要用这种 this kind of heat engine。所以这个就是它们的不同和它的工作原理。Yeah. Okay, at this point, any problems? Chart. Maybe you can talk more about with test. Oh, guys. For the test, Professor Liang will tell you more information later. So he will send you emails. So okay, wait for his information. Okay. Test 就是 Professor 梁会告诉你们就是更多的 information， 你们就等一下哈。然后就是事实上，燃烧在真正的发生in the real engine, the process is the real process is literally complicated， 就相当的非常的复杂。但是我们 from the point of view of thermodynamics， 你从热力学的角度上，我们现在是不关心就是 combustion 的，我们先把它放到一边的。然后我们去看一下，我们现在关心的是对于一个 cycle， 对于这个 cycle 或者是对于这个 engine itself， 我们想知道就是它的 thermal efficiency 是多少。所以就是我们想办法要把 combustion 你先放到一边，我先去看这个。如果我想再研究 combustion 呢，我再把这个放到一边去研究这个。所以就是说我们先看 thermal efficiency。那所以第一个假设呢 ，the first assumption is that there is no combustion occurs inside your cylinder， 就是我们的 combustion 不再在这个 cylinder 里面发生了，它会发生在外部。我们就说我们给它一个热源，一个 heat supply， 我们去模拟去 model the heat produced by the combustion。这样子我们就说我们不用被那个 combustion efficiency 影响到，就是不关心它了。再一个就是还有一个比较麻烦的事情就是你的气啊，你进来的是油，空气，你燃烧之后 what you have is CO, CO2, H2O, or the nitrogen, right？ 你会剩下这些气体，它的 property 是一直在就完全变了，你是没有办法进行这种 basic analysis 的。所以我们另一个 assumption 就是说，我们用 air 来作为它的 working fluid， 我们不再讨论很复杂的东西，我们把它简单化。这样子我们可以把它假设为 perfect gas， 我们就可以now we can perform our analysis， OK， 然后同时的话就因为你是 air 了，你没有 fuel 了，所以就是说是我就不需要呢 intake stroke 和 exhaust stroke， 所以就是你现在有的嘛，就是变成了一个事实上 in reality 它不可能是一个 non-flow system， 因为你有进气，你有排气，但现在你永远有 air 了，那就说明呢，我可以变成一个 non-flow system， 我们就可以开始去研究它。而且呢，在任何的 cycle 或者是在 thermodynamics， 我们都经常会假设一个什么 no loss， 理想化嘛 ideal model， idealize our problem， 不然我们没有办法，我们会忽略一切 loss，不管是热的，还是说你这个流体带来的这个摩擦呀引起的这种耗散，我们都忽略它，这样子我们才可以去分析。所以呢，我们就建立起了 finally we built up this ideal cycle to perform our analysis。这整个过程就是你给一个 work input，push your piston，然后去压缩 the air inside，然后它就会从低压低温的气体 air 空气变成一个高温高压的气体。在这里呢，我们开始给它一个 heat supply，we add heat into the system。但是这儿你一定要注意的是 ，you should pay attention here。You have heat supply at constant pressure。哦，我把这块讲完，咱们休息一下。在那个 gasoline engine 的时候，我们那个理想的模型就是 air standard auto cycle，那是 constant volume，就是说是我们假设它是不动的，然后就我们可以忽略它的那个 piston 的 movement，然后给它一个 heat supply。但这里要注意的是，我们是 constant pressure，就是 pressure is constant，然后你把它推出去。它就有一个那个，它一边提供热量，一边给你一个这个 work output，这是一个同时进行的过程，所以是 constant pressure。在这个期间呢，因为你要保持压力不变，你必定是要 expansion。You have to have the expansion to keep constant pressure。这算是一个 constant pressure 的过程，这是跟我们上一个 cycle 最不一样的地方。然后 process 3 to 4，就是这个就跟上一个一样了，就是跟 auto cycle 是一样的，它会开始膨胀做功，这个就是又一个 isentropic process。在4到1的过程中 ，process 4 to 1 at constant volume we reject heat， 就是在 constant volume 等容的过程中，我们开始放热，把热放出去，废热嘛 ，heat reject， 就是这3个过程，其实跟上一个都是一样的，只有这个过程，就是它是一个由 constant volume 的变成了一个 constant pressure 的。好，这个就是它的整个过程。If you have any problems, ask me, and let's take a 5-minute break, okay? Feel free to ask me if there are any problems, okay? Any problems? No, good.
For those who are facing your computers, any problems? Okay, let's make a start again. I have already shown you how to derive these equations for isentropic compression, right? We have the characteristics of isentropic. So use this by combining the characteristics of isentropic compression with the perfect gas property, we can derive these equations. You should remember these equations to help you solve problems, okay? For isentropic compression, okay? Now, we are here. The constant pressure heat supply, that is process 2 to 3. What we have is constant pressure. So we have P2 equals to P3 equals to P2, okay? Also, what we have is the non-flow energy equation. That should be Q minus the work output. Pay attention. We have work output. We have water output during this process because it is constant pressure. We have movement of the cylinder, so we have the work output equals. Give you another opportunity. Will this give you a chance? Again, H1, H2, H. U2 minus U3. Yes, always remember, pay attention, the final state minus the initial state. Otherwise, you may have problems in your calculation, okay? Here we have heat supply. We also have water output. We cannot reject any of them. We cannot cancel any of them. What we should do for the piston and cylinder, what is your work output? The definition for the work is what? PdV, right? Remember this? The definition for work. Okay? Here, what we have, P is constant, right? So we can take it out. That is P dV. What's this? P V3 minus V2. Okay? That is the work output drawing process 2 to 3. Let's plug this definition into this equation. What we have is Q equals plus specific volume. Let's rearrange it. That should be what's this? What's this? What's this? Who know? What's this? Anyone know? Yes. This is enthalpy. The definition of enthalpy, right? Enthalpy. So what we have now becomes H3 minus H2. How to calculate enthalpy for a perfect gas? What is for a perfect gas? Yes, specific heat at constant pressure T3 minus T2. Again, if we know the temperature, we can calculate the heat supply. We have P3 equals P2. We also have the property of perfect gas. What that? PVT equals constant, right? So by plugging this this relation into this equation, what we get? We can get the sorry, should be constant, right? Sorry, constant. Rearrange it. We can get the T to V ratio. At this point, any problems? No problem, okay? Actually, these are the contents in chapter 1. If you don't remember it, if you don't remember them, go back to check chapter 1 to review chapter 1, okay? Here we have another important definition. Again, we have a volume ratio. For this ratio, we call it cut-off ratio. Yeah. Cut-off ratio. Usually we use RC. Cut-off ratio. Another important definition of the ratio of volume. Cut-off ratio. You should remember these equations. Okay? For the constant pressure heat supply for this process, what we have is work done equals 2P times the difference of volume. Also, we have heat supply. Here you should pay attention. Work done is positive, and heat supply also the positive, because the direction. Heat supply to the system is positive. Heat reject from the system is negative. Work done, but the system is positive. What input to the system is negative because of the direction. By using the non-flow energy equation, we can calculate the heat supply. And also, by combining the characteristics of this process and the property of perfect gas, we obtain the temperature to volume ratio. Here we have another important definition, cut-off ratio. It is refers to the ratio of V3 over V2 divided by V2. That is our cut-off ratio. We usually use RC to represent it, okay? Process 3 to 4 is isentropic expansion. I have already derived the equations for isentropic process. So here, you need to remember these equations. This one, what we have for the compression ratio, V4 to V3, we can rewrite it as the ratio between the compression ratio and the cut-off ratio. You should remember it, okay? The last process 4 to 1. Oops. We have constant volume heat rejection. Constant volume, that means no work because we do not have any displacement. V4 equals V2 because it's a constant volume process. This is the characteristics of this process. So by combining this equation with the property of perfect gas, again PV over T equals constant, we can get the T to P ratio. That should be T4 equals T1 times, should not use this. P4 over P1. Okay, this is T to P ratio. The work done during this process, equals to zero, right? No displacement. So that, therefore, we have should be M, the final state minus the initial state. So again, there's no work done. So the heat reject equals to, right? This is a property of perfect gas. You can calculate the heat rejection now. Okay, this is a process of constant volume. Again, you should remember these equations to help you solve your problems. At this point, any problems for this full process? Any problems? any equations that you don't know how to derive it. For those who are facing your computer, can you follow? Can you follow? I see, thanks. Yeah. Yes, it's specific volume, V over M. We get the specific volume. Any problems for those who are facing your computer? If no, I will continue. Okay. Okay, let's move on to the thermal efficiency. As I said, our major concern for a cycle, for an engine, for a heat engine is the thermal efficiency. Because we use thermal efficiency, we can know its performance. Okay, so, and according to the second thermodynamic law, the second law of thermodynamic, you can never convert all of heat supply into work output. So the definition of thermal efficiency should be your outcome divided by your payment. Because when we talk about efficiency, we always use the ratio between your outcome with your input or your payment. The outcome here is our net watt output. Our input or our payment is the heat supply, right? So that's the definition of thermal efficiency. For this cycle, the net work output divided by the heat supply. For the first dynamic, according to the first thermodynamic law, what we have is, for a cycle, the net work output equals the net heat supply, right? Remember this? This is the first thermodynamic law. This is a thermodynamic law. So what we have here is the thermal efficiency equals the net heat supply divided by the heat supply. What is? It should be the sum of your heat supply and heat rejection. Here you should pay attention. This Q reject, this reject heat is a negative value. It is a negative value because the direction, the heat is reject from your system. So it's negative value. We rearrange the equation, we can receive the definition of thermal efficiency as this. You can use both of the definitions to solve your problem. You can use this one. You can also use this one. For this cycle, we have already performed the analysis for each process. So what is Q reject? What is the reject heat? Reject heat is what? Q for 1, right? Q for the heat supply is Q 2, 3, right? Remember these equations? We have already know how to calculate this heat, the heat supply or the heat rejection by temperature, right? Remember that? So it should be Q41 should be mCV, the specific heat at constant volume. Yes, good. For this CP, yes. Here should be CP. 2. We can reject this term and rearrange this equation. We have okay, down. Now, if you have the temperature at each point, you can solve everything. You can know the value of your thermal efficiency. That's the thermal efficiency for this air stand diesel cycle. Here you should pay attention. The heat reject is a negative value. Negative value. Guys, you should remember this definition. You should remember how to calculate the thermal efficiency, okay? You need to remember these equations. As I said, you can use both the definitions. You can use this one to calculate, or you can use this one or use this one. But you need to remember them, okay? In the previous lecture, we gave you another definition, important definition. A measurement effectiveness of your cylinder. The mean effective pressure. Remember this definition? Do you remember it? This value refers to the performance of your cylinder. A higher mean effective pressure refers to a smaller cylinder that can produce the same network output. It's a measurement of the effectiveness of your cylinder. It is defined as the net work output divided by the swept SWEPT, yeah, swept volume. Okay, sorry. Swept volume is the volume sweated by the movement of piston. So that should be the maximum value minus the minimum value. Sorry, the difference between these two volumes. So that should be V at the bottom dead center minus the top dead center. For this cycle, it should be V1 minus V2, okay? The maximum value minus the minimum value. This is a swept volume. The swept area, the volume by the movement of your piston. Again, we have the net work output. It equals to the net heat supply according to the first thermodynamic law. In the last slide, we have know how to calculate it. Well, that should be right. The sum of your heat supply and heat rejection. For this, sorry. What we have now is, let me show you this first. This is compression ratio, right? So we can rearrange this equation as this. How to calculate V1? By using the property of perfect gas. P1 V1 equals M times R and T1. By using this equation, we can calculate V1. And Q, the heat supply and heat reject, you already know the equations, right? You already know how to calculate it. So let's put everything into this equation. What we have is CP. M RT1 divided by P1 P, because we have a non-flow system. The amount of air do not change, so we can cancel this term. Now this is a definition of mean effective pressure. Sorry, it should not be the definition, should be the calculation, the representation for this diesel cycle, air standard diesel cycle. Okay. At this point, any problems for these equations, for these definitions, any problems? If no, we are going to go through the class tutorial. Any problems? For those who are facing your computers, do you have any problems? No? No problems? Okay. Okay, guys, you should remember these equations and you need to remember this definition for the mean effective pressure. It is the ratio between your network output divided by the swept volume. Okay? Okay. This is our class tutorial. Question 19. We have a four-stroke diesel engine. We want to analyze the engine with the air standard diesel cycle theory by using this theory. The engine has a compression ratio of 16, and the minimum cycle pressure and temperature are 1 bar and 15 degree C respectively. Assume heat supply into the cycle is 1,350 kilojoule per kg of air. Determine the following: the maximum cycle pressure, the thermal efficiency, and the mean effective pressure. Please prepare yourself a piece of paper and we will start. and as well as your calculator. Okay. First thing, when you see a problem with these words, air stand diesel cycle, the first thing you need to do is to draw a PV diagram to help you solve your problem. So first, let's draw the PV diagram. Maybe here, B, P. We can directly draw the PV diagram according to the non-flow process of the air stand diesel cycle. That is 1 to 2 isentropic expansion, compression, isentropic compression, and constant pressure heat supply. Then isentropic expansion. The last process, constant volume. Point 1, 2, 3, 4. Isentropic means no heat, and we have characteristics PV gamma equals constant. For the compression, isentropic compression, we have a work input. Constant pressure, we have a heat supply. At the same time, we have a work output because we have the movement of piston. Isentropic expansion, what we have is a work output, the useful work output. Constant volume means there's no work. Instead, we have the heat rejection at constant volume. That is our PV diagram. P3 equals P2. First thing, draw the PV diagram. Okay? Then, next step, let's write down the known values. First, compression ratio, RV equals what? V1 over V2 equals 16. Okay? Minimum cycle pressure. What's the minimum cycle pressure? Try to find the minimum cycle pressure in your PV diagram. That should be P1 equals 1 bar. Here, I will suggest you to change your unit to kPa because we use air as our working fluid. We have the perfect gas. Sometimes you use bar, you can get the right answer, but sometimes you will get the wrong answer. I will suggest you always use kPa in order to avoid any error may cause. Okay? So let's change it to kPa. Okay? The minimum temperature is 15 degrees. That should be T1. T1. Here, pay attention. You must change degree C into absolute temperature because you are dealing with perfect gas. You should always use absolute temperature. You should always use K as your unit. So let's change it. What's the number for the absolute temperature? You can tell me? Good. The heat supply into the cycle is 1,350 kilojoule per kilogram. That is Q23, right? This is our heat supply equals kilojoule per kg. These are our known values. Let's start to solve our problems. First, the maximum circle pressure should be P2 or P3 because we have a constant pressure process. So here, I will suggest you to solve this kind of problem step by step, from point 1 to point 2, and point 2 to point 3, from point 3 to point 4, and then go back to point 1. Do not jump any process. Otherwise, you may have some errors, okay? You may have some wrong results. Do not jump. Follow the process step by step to solve your problem. Then let's start. Process 1 to 2. Isentropic. So we have PV gamma constant, right? We know P1 is 100 kPa. Pay attention here, we changed the unit. Also, for T1, we change it into absolute temperature. We also know the compression ratio is 16. So now we can calculate the temperature at point 2. We use the temperature to volume ratio. That should be what's the number? What's the value? 873. Yeah, good. K. Pay attention. K. We use absolute temperature, drawing the whole process of the solution. Okay. Always remember to use K, absolute temperature, and absolute temperature. Now we can calculate the P2, the pressure at the point 2, by using the P to V ratio, the pressure to volume ratio. That should be right for this. KPA. Okay. Check. Sorry, guys. I think it's something. No, no, it's okay. Okay. Remember, I have shown you the equations, the P to V ratios. We use the compression ratio here. Okay, we use these equations to solve the problem. Now we know the properties at point 2. What we, oops, sorry. Let's go to process 2 to 3. We have constant pressure process so that P is constant. We have P3 equals P2, right? Remember that for the heat supply, it equals to mCp T3 minus T2. Remember the equations? I have already derived it for you. Here we have the work output, we have heat supply. We rearrange the energy, the non-flow energy equation. We get this result for the heat supply. Let's plug these numbers into this equation. What we have is we know the heat supply, right? Here we have the heat supply number. Okay. E. Here I should remind you, see the heat supply is kilojoule per kilogram. Okay. So I think it should be right like this. Okay. Kilojoule per kilogram, right? If the heat supply, it should be kilojoule, but we have kilojoule per kilogram. So let's CP, we have 1.005. For T2, we know the value. We have already calculated the value, so it should be 873 K. Then we can calculate the temperature at point 3. But the number should be the number should be 2,200. Okay. Now we have the pressure at point 3. Let's calculate the cutoff ratio. It should be T3. Oh, anything wrong? Let me check. Anything wrong? Here? No, okay. V2 equals, remember the relationship? What's wrong? No, okay. What's the value? What's the value, guys? The cutoff ratio. It should be cutoff ratio. What is? Yes, 2.5. This is our cutoff ratio, another important definition. Okay. For process 3 to 4, again, we have an isentropic process. So we have PV gamma equals constant, right? So we can use the relationship between the temperature between the temperature and the volume. We can calculate the temperature at 0.4. Gamma minus 1 should be, sorry. Sorry, I should derive this one. Use the, do not use this one. Sorry, guys. I may explain to you in this way. Okay. V3 over V4 equals what? V3, V2. We can rewrite it as this or this. This is RC, this is RV. Cutoff ratio and compression ratio. So we rewrite our equation. What we have is okay. We plug this into this equation. That's what we have by using the cutoff ratio and the compression ratio. Okay. We know we have already calculated the cutoff ratio and we know the compression ratio. We can calculate the temperature at 0.4. Okay. At this point, any problem? Wrong. Where? This one? V2, yes. Sorry. 1 over combustion ratio. Okay. That's. Sorry. I'm so sorry, guys. Let me check. What's wrong with my result? It seems something wrong. I'm sorry. I'm sorry, guys. Oops. Oh, the V3, V2, V2, V4, right? I mean that. But remember, V1 equals V4. is a constant volume. So we can rewrite it. Sorry, I should not jump this step because V4 equals V1, okay? That means should be, this is the cutoff ratio, and this is compression ratio, 1 over compression ratio. Let's plug this equation into this equation. What we have is gamma minus 1, okay? At this point, any problems? Any problems? Yes, because we have a constant volume. Constant volume. V4 equals to V1, yes. This one? 这个吗？上面。这个是吗？啊 ，sorry， 这个啊，我以为是这里 ，sorry。V4 equals to V1 because we have a constant volume. Okay, so we rewrite the ratio of V3 to V4. We have the ratio, the cutoff ratio and the compression ratio. Okay. Any problems here? If no, I will continue. Okay. So for T, we know T3. And we know the cutoff ratio here. What's the number? Guys, please calculate for me. What? One more thing. Good. Here you should pay attention. We rewrite the ratio of V3 to V4 by using the cutoff ratio and compression ratio. Here, V1 equals to V4, okay? Now we know the temperatures at each point. We know T1, T2, T3, T4. As I said, now we can solve everything. We can calculate the thermal efficiency, the mean effective pressure. Now we can calculate everything by using this four temperature. The temperature at 4 points at all these 4 points. Okay. Let's answer the question first. The maximum cycle pressure, that should be P2 or P3. We already saw it. So for question A, the answer should be P maximum equals P equals KPA. Okay, KPA. Second question is the thermal efficiency. For the thermal efficiency, the definition should be 1 plus you should pay attention here. Rejection heat is a negative value because the direction. I have already derived this definition for you, this equation for you, okay? what is heat rejection should be Q. We already know the heat supply, okay? So for the heat rejection, we need to calculate heat rejection. It should be but here we have a problem. We have the mass, but we don't know the mass of the air. We don't know the amount of air, or although we know the value of Q, the heat supply, but we can reject it. What's wrong with this? Okay. Sorry. What's this? What's wrong with this pencil? T4 minus T1, that should CP T3 minus T2, okay? For this equations, any problems? Sorry. Here, okay, it's better. Okay, any problems for this? Sorry. Sorry, guys. I'm so sorry. What's wrong with me? I'm sorry. Okay, for this equation, any problems? Okay. Good. Always the final state minus the initial state. I'm so sorry. That I don't know what's wrong with me. So let's rewrite it. It should be CV. What's wrong with this? Now we can reject this term, and we can calculate the thermal efficiency. CV should be yes. This should be write down the numbers. Okay. The number should be like that. Should be about 0.58. Sorry. Okay, I cannot make any mistake anymore. Okay. PM equals to what? The definition, the network output divided by the swept volume should be V1 minus V2. Okay. So for this net work, you can use the definition of the thermodynamic, the first thermodynamic law, that you can use the sum of Q are the rejection heat with the supply heat, the sum of these two heat. You can use this one to calculate, or you can also use the thermal efficiency. You can use, they are the same, right? They are the same because the thermal efficiency, remember that, it should be, okay, you can use both of them. You can use both of them, okay? Then for V1, I have already shown you how to calculate V1. It should be MRT1 P1, okay? Let's put it into our calculation. For the QS, we have M times, the number should be because the heat supply, the unit is kilojoule per kilogram. So for the heat supply, it should M times this number, okay? So we have this one, and times should be the thermal efficiency. And again, we have V1 for this, okay? Because V1 compression ratio, okay? We plug this definition into the equation. What we have is M PR T1 P1. We reject this term. We know R T1 P1 equal to times okay. Guys, what's the number? What's the number? Who can tell me? What's the result? 1,000.1027. Good. So solved. At this point, any problems? Here, I make a big mistake. I use T4 minus T1. Okay. You should always use the final state minus your initial state. Okay. But you are good. You point out the mistakes. Okay, good guys. And here, you should pay attention. We use RC over RV to replace the ratio, the volume ratio of V3 with V4, because we can rewrite it on this equation, and we have V4 equals to V1 because we have constant volume. Guys, you should know at this point, you should be able to draw the pH diagram first. Then you should be able to perform this basic analysis for each process. And first thing, you need to remember you must use absolute temperature. Always use absolute temperature because you are dealing with air, the perfect gas. So please do remember to use the absolute temperature. And for the pressure, I still suggest you to use kPa to avoid any error may occur. So first thing, change your unit for temperature and pressure into K and kPa. Okay, that's the first thing you need to remember. The second thing, do not jump any step. You should perform the analysis from point 1 to 2, 2 to 3, 3 to 4. Do not jump any process. Okay. That's the diesel, the air standard diesel cycle. Okay. At this point, any problems? For those who are facing your computers, any problems? If no, I will move on to the next topic, refrigeration. Any problems? We'll talk about the group project. Actually, I obtained the material, maybe the related material for the group project. I will upload it to model for you, but I actually from Professor Liang. I'm not sure it is the same vision as yours. Have you？这就是你们现在有的那个 material 是 AC project 的有吗？你们那个有？就我有的也是你们有的，就是我也没有额外的那个，我可以给你们show一下，就是那个。Where is my USB? Sorry, where is my USB? Okay, let me show you the. Right. Professor Liang gave me this material today because the part-time students always said there is something wrong when they download the AC project in Moodle. So I asked for this material, but I'm not sure it's the same as yours. Is the same as yours? Yes. 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 Yeah. That's all. That's the material I have. So sorry, I cannot help. That's the requirement for you. Okay. Okay, at this point, for the air stand diesel cycle, any problems? If no, we will finish this power gas power cycle. Okay. 加油，加油！我是人加油。Refrigeration for me. Okay, thank you. I'm sorry. I have some mistake. Sorry. Actually, I'm a little nervous. But if you 就是你们如果听不明白，你们可以跟我讲，我再给你们讲。就是我有点紧张的时候，我可能就会讲的有点不清楚，你们可以告诉我 ，so sorry 。然后 ，OK, we still have 5 minutes. OK, refrigeration cycle. OK, 剩下5分钟，那我跟你们讲，你们看过那个电影那个天能吗？Tenant. OK. Yes, okay. You, sorry. We have class here. Okay. I want to talk to you that film because in the refrigeration cycle, the main function of the refrigeration is to remove heat from the low temperature region and reject heat to the high temperature region. In nature, you know that will never happen, right? Because according to the thermodynamic law, heat can never pass from a colder to a warmer body naturally. But in that film, everything is reversed, right? Involving time, heat transfer, also the fluid flow. By using the machine from the future， 就是他们未来的那个机器，可以就是时间倒转，也可以让你的 heat transfer 反过来。我们的热力学定律在这个世界，这是我们的规律。这个低温物体和高温物体，如果是自然发生的，那一定是从高温传向低温，对不对？但是在那个电影里，它 reverse 了，就反过来了嘛。但是 unfortunately, up to now, we don't have this kind of machine from the future human. So we still obey the thermodynamics law, right? 那我们没有那个机器嘛，那我们还是要遵循我们的热力学定律，对吧？所以这就是，如果我们想实现制冷，那我们就需要 we need payment, right? 那就是我们需要 what work input. Okay, that's all for today, and let's continue in the next lecture. And I'm sorry today I'm a little nervous. If you have any problems, please feel free to ask me, okay? For those who are facing your computers, any problems? If no, I will leave Teams. Please feel free to ask me. And I'm sorry for any mistakes. Okay. Okay, see you in the next week.